Hello, welcome to another module in this massive open online course. So we are looking at example problems for the Laplace transform. Let us do a few more, or in fact one or two more, and then we'll go on to a new topic. So I want to start with another example problem for the Laplace transform. The problem is the following. So this is problem number 7. Consider the RL circuit that is given below. So I have a current source which is conducted in parallel with a resistance R and inductor L, correct? And if we call this as output current ILT equals Y, and if we call this as IT, then we have VT equals L DILT T by dt, okay. And if you call the current through the resistance as IRT, we have therefore by Ohm's law IRT into R equals VT equals L DILT by dt, which implies IRT equals L over R DILT over dt, and further we have the IT current equals IRT plus ILT. This is current through resistance, IRT plus current through inductor ILT, which is equal to L by R DILT by dt plus ILT, okay. So this is my input IT. So this is the input output equation, okay. So if we denote ILT by XT, this is my input XT. So I have XT equals the input, which is IT, and of course we have already said that ILT is the output, that is Y of t. So the input is the source current, that is IT, and the output is the inductor current. Output YT is the inductor current, that is ILT, okay. And now therefore we have XT. Writing this in terms of XT YT, we will have XT equals L by R d over dt YT plus YT. Now with taking the Laplace transform, we have XS equals L over R. Remember, Laplace transform d over dt YT is S ys. This is SYS plus the Laplace transform of YT, which is YS, which is equal to, well, YS into 1 plus L over R into S, which means the transfer function, remember the transfer function, input output transfer function is defined as ratio of output Laplace transform to input Laplace transform, that is ys over xs. Therefore, hs, the Laplace transform of the transfer function is basically Laplace transform the impulse response, or basically the transfer function is basically ys by xs equals 1 over 1 plus L by R S. So, we have Hs equals 1 over 1 plus L by R times S. And observe the pole of this system. Now, this can also be written as R over L divided by S plus R over L. So, the pole, it has a one pole P1 equals minus R over L. Therefore, ROC, now let us assume a right handed signal. Therefore, ROC is basically, if ROC is basically for a right handed signal, ROC is basically S greater than minus R by L, and the corresponding inverse Laplace transform, that is HT, you can see is basically that is R over L times e raised to minus RT over L ut. Okay. So, this is the okay. So, this is the impulse response. Okay. This is the impulse response of the RL circuit. Okay. So, basically we have found the impulse response of this RL circuit, which is R over L e raised to minus R t over L times ut, assuming that it is a right handed signal, and the ROC is real part of S greater than minus R over L. Okay, all right. Now, let us proceed on to a different topic, which is something that we are going to discuss briefly and something we did not discuss before, that is the concept of the unilateral Laplace transform. Remember, what we have looked at so far is the concept of a bilateral Laplace transform. The unilateral Laplace transform or one-sided Laplace transform can be defined as follows, that is xi of S equals 0 minus to infinity xt e raised to minus st e raised to minus st dt. Okay. And therefore, now the ROC, now look at this, we are clearly considering a right handed signal, therefore, ROC is of the form, when we are looking at the unilateral ROC, we are considering a right handed signal. So, ROC will be of the form real part of S greater than sigma max. Now, typically this is useful for determining the response of a causal system to a causal input with non-zero initial conditions. All right. So, the unilateral Laplace transform or the one-sided Laplace transform, as we are going to illustrate, is basically very useful in scenarios where you have a causal system with a causal input and non-zero initial condition. So, this is useful for the unilateral Laplace transform useful for a causal system with a causal input. Remember, causal input is non-zero only for t greater than equal to 0, plus where you have non-zero initial conditions. Alright, now some of the properties of this unilateral transform are as follows, slightly different from those of the bilateral Laplace transform. So, let us say the signal x t has unilateral Laplace transform x I of s, then dx t over dt, the derivative has Laplace transform s x I of s minus the value of the signal x at 0 minus. So, this is the derivative, that is, remember previously for the bilateral we simply had the Laplace transform of the derivative of the signal is s x s, but here we have s x I of s, where x I of s is a unilateral Laplace transform minus x of 0 minus, that is the value of the signal at 0 minus. Further, if you consider integral 0 minus to t x tau d tau, this will have the Laplace transform x I of s divided by s, and integral minus infinity to t x tau d tau will have the Laplace transform x I of s over s plus 1 over s integral minus infinity to 0 minus x tau d tau. So, these are some of the properties of the unilateral transform. Let us look at an example to understand this better. Let us consider the RC circuit below. Consider the RC circuit where you have a voltage source connected across a resistance and a capacitance in series. So, you have this, let us say, is the voltage, VCT is the voltage across the capacitor, VRT is the voltage across the resistance. Let us say we assume a current of IT, let us say the source voltage is given by VST. Okay. Now, we are given the initial condition Vc 0 minus equals V naught. Remember, this is the initial condition, this is the initial voltage of capacitor. Further, we are given that the source voltage equals V times ut, that is, the source voltage is as follows. So, we have a step change, at t equal to 0, we have step change to V. So, this is basically your Vs t, okay, the step function, okay, at time t equal to 0 it becomes V. So, it is V times ut, and the initial capacitor voltage, that is Vct at t equal to 0 minus, is V naught, okay, the initial voltage across the capacitor is V naught. Okay. Now, we are required to find what is the capacitor voltage for time t greater than or equal to 0. How does the capacitor voltage change as for time t greater than or equal to 0. So, we are required to find what is Vct equal to for time t greater than or equal to 0. Now, taking the unilateral, now what we can write this as from the system, the voltage across the capacitor. Now, you can clearly see the voltage across the capacitor plus voltage across the resistance is equal to the source voltage. Now, you can see the voltage across the resistance equals I times the resistance, correct, IT times the resistance, but IT equals, we have C dV dVct or dt, that is C times the derivative of the voltage across the capacitor, that is the current, which implies the voltage across the resistance equals R C dVct over dt, which basically now implies, substituting this here, we have Vct plus R dVct or dt equals Vst, which is given to be V times ut. Now, we take the one sided Laplace transform on both the side, okay, because we have a system with non-zero initial conditions. So, we are using the one sided or the unilateral Laplace transform. So, taking the unilateral Laplace transform, so taking the unilateral Laplace transform, the unilateral Laplace transform of Vct, let us say is Vcs plus the unilateral Laplace transform dVct dt, as we have seen before, is S Vcs minus Vc0 minus, which is V naught, equals the Laplace transform of Vut, which is V over S. This implies that we have Vcs plus RC Vcs minus V naught equals V over S, which implies Vcs into this is S Vcs, Vcs into 1 plus S RC or 1 plus RCS, let us write it that way, 1 plus RCS, Vcs into 1 plus RCS equals RC into V naught plus V by S, implies Vcs equals RC V naught by 1 plus RCS plus V by S into 1 plus RCS. Now, further simplifying this, this is simply V naught over S plus 1 by RC plus V into 1 over S minus RC over 1 plus RCS, correct. So, you have this equals, now again, which if you take the inverse Laplace transform, you get Vct. Now, the inverse Laplace transform is V naught over S plus RC is V naught e power minus T over RC into ut plus V into inverse Laplace transform 1 over S is ut minus inverse Laplace transform of RC over 1 plus RCS is simply e raised to, again similar to before, e raised to minus r over c uh, 1 minus e into e raised to minus t over r c u t. So, V c t equals this, which is equals to taking inverse L t. Okay, and taking the inverse Laplace transform. So, this is V naught e raised to minus t over r c plus V 1 minus e raised to minus t over r c into u t, which means for t greater than equal to 0, V c t equals, we have V c t equals V naught e raised to minus t over r c plus V into 1 minus e raised to minus t over r c for t greater than equal to 0. Remember, this holds only for t so this is output for t greater than equal to 0, and therefore, using the inverse Laplace transform from the differential equation of the system, using the concept of the unilateral Laplace transform, or basically the one sided Laplace transform, we have been able to find the output for t greater than equal to 0 for a system with non-zero initial conditions. All right. So, in this module what we have seen is, we have seen different problems as well as the concept of the unilateral Laplace transform. So, we will stop here and continue in subsequent modules. Thank you very much.